Hey friends, it's good to be back with you. In this video, I'd like to finish up first and second order systems, which means first and second order ordinary differential equations. But this time I want to do it exclusively in MATLAB. If you go to the previous video, you'll see that I did a lot of the work in MathCAD just because it was easier to type out and easier to look at. Most of the time for heavy-duty number crunching, you're going to be using MATLAB. And it's very powerful, I recommend it, but there's a little bit of syntax you got to understand first. So let's start with the governing differential equation from the previous video. Okay, we've seen this before. This is just Newton's law written out for a vibrating system, which in the previous video was a spring, a weight being supported by a spring and with a damper, shock absorber. And we decided to let that be zero, although you don't have to. So physically what we're going to do is we have a weight hanging from a spring and a damper. Pull it down and just let it oscillate for a little bit and watch it damp out. That's all we're trying to do. Now, this is fine. This is a second order system. The big idea here is that MATLAB only knows how to solve first order systems. So how do I do that? Well, there's this tool called state space. Now, it's not my favorite name, but it's the one we're stuck with. And it's a way of just writing down a second order system as a combination of two first order systems. It's really straightforward. So MATLAB wants to see some variable x dot equals some function of x and t. That's the format it wants. Well, I have an x double dot. Where does x double dot go in there? Well, what I'm going to do is I'm going to make up another variable. Let's say you call this maybe a dummy variable. And I'm going to say y equals x dot. All right? I'm just going to do that. And so what I'm going to do now is write this out as a system. I'm going to say x dot equals y. And y dot, which that's actually x double dot, see now we're getting somewhere, is minus c over m y minus k over m x. All right, so see there's no derivatives on the right-hand side of the equation anymore. So this becomes a system of first order equations, two first order equations. Now I got to do one more thing here. MATLAB likes to think in terms of vectors. So I'm going to rename a couple of things here. I'm going to say y is just x2 and x is x1. So everywhere I see y, I'm going to just rename that x2. And everywhere I was x, I'm going to write out x1. Fix that. There. Now it's in vector form. So I'm going to have x sub 1, x sub 2. It's going to be a vector of variables. So that's the equation that I'm going to type into MATLAB. And I'm going to use the same values of m, c, and x that we had before. And I'm going to solve it over the same time span of 0 to 20 seconds. Okay? With that in mind, let's go to my computer and see how this works. Okay, I've started up MATLAB. And I've written a small function. You can see right here, I've said d equals, d2x dt2. That's the name of the function right here. You can see it there, and you can even see it down here in the current folder. That's its name. D, this capital D, that's the vector right there that describes the differential equations. So let me just walk you through this. So I've got mass equals 1. Damping, C equals 0.1 as before, and K equals 10. And right there, let's probe this a little bit. Right there you can see there's that x2 that I had on the board. There it is again, and there it is again. Or there's x1. So what I've got is just simply the right-hand side of the two equations. It assumes that what's on the left-hand side is x1 dot and x2 dot. So it doesn't need to know what those are. So far so good. This isn't looking too complicated. If there's one complicated step here, it's the statement that actually calls that function.
Here's what it looks like, and it took me a couple of tries to figure this out when I went on MATLAB help. But once you get the hang of it, it's not too bad. So there's ODE45. There's a bunch of different solvers in MATLAB, and this one's actually called a fourth, fifth order Runge-Kutta. If you have an initial value problem and you don't know what else to use ODE45. In fact, you probably need a reason to use anything else. There are reasons, but this is always your starting point. I think it even says that in the help file. If you don't know what else to use this. Now right there is probably the confusing part. I'm calling this function up here d2x dt2, and I'm having to put that ampersand in it right there, making it look like it's kind of an anonymous function. It's not intuitive, but it does work fine. Now after that, you're home free. This is the range of time, so 0 to 20, just as we had before. And this is the initial condition. So remember, x1 is position, that's 1, and x2, which is x dot, is the velocity. So the position is 1, the velocity equals 0. So all I have to do is run it now. And so I've got two variables here, t and x. So it's got time and x, but now x has two columns in it. Well, I gave it two differential equations, so it's going to give me two answers. You got to decide which one it is that you want to look at. The first column will be x1 and the second column will be x2. Well, I want to look at position, and position is x1, velocity is x2. So I'll pull up this plot command I did before. And so time plotted against the first column of the x matrix. So all the rows, first column, I'll make it trace color blue and turn on the grid. And there's what it looks like. Well, that looks pretty good. How does this look up here? Does it look like I've got about the right answer? It does. Okay. Now, it guessed at how many points it needed to give me a correct answer, an accurate answer. So let's turn on marker for a second and just take a look. Now you can see over here, there's 349 points. What does that really look like here? Well, a reasonable number. So that sure looks like the right answer. And there we go. So there's a second order system. All you would have to do to turn this into a first order system is set m equals 0. Now, if you set m equals 0 right here, there's a pretty good chance you're going to wind up with some numerical conditioning problem. Better to remove m from the differential equation to start with. And when you do that, you're not going to have second order anymore. You're going to have first order, and you don't have to go into state space. Now, you should be able to use this example as a template for problems of your own, equations of your own that are also second order. I hope this helps, and we'll talk to you next time.